The late 19th century saw the birth of the electrical grid. Massive dynamos began churning out raw power on an industrial scale, lighting up cities and driving factories. But the companies generating all this energy faced a fundamental commercial hurdle. Unlike physical coal, water, or gas, electricity is an invisible flow. It cannot be put in a bucket, it cannot be weighed on a scale, and it cannot be handed to a customer as a physical receipt. To make the power grid a viable business, utility companies needed a way to track consumption. They required an accurate meter, a device that could translate an invisible flow into a tangible, billable number. Nikola Tesla tackled this problem not as a theorist, but as a practical engineer. While he is often associated with giant, sparking coils, he devoted significant effort to this specific billing challenge. In Chapter 35 of his extensive patent catalog, he describes his solution for this task, the electrolytic registering meter. The success of the modern power grid relied just as much on the ability to quantify and measure the invisible as it did on generating the power itself. Solving this measurement problem required a shift from the macro-scale grid to the micro-scale engineering of the laboratory bench. The meter's architecture is simple, a conductive rod immersed in a chemical solution. Measured electrical current flows directly through this conductor, initiating electrolysis. The current forces metal ions from the liquid to physically attach to the rod's surface. This chemical reaction transforms a fleeting electrical flow into a tangible, permanent accumulation of matter. As more metal attaches to the conductor, the physical rod becomes thicker. This change in thickness fundamentally alters the rod's electrical resistance, the measure of how much a material opposes the flow of current. A thicker wire allows the electrons to flow much more easily, while a narrow wire heavily restricts their movement. In Tesla's design, the change in the conductor's resistance occurs in a strict, definite proportion to the strength of the electrical current. This linear relationship allows the utility to calculate usage with mathematical precision. If the current flows in the opposite direction, metal is stripped away from the conductor, making it thinner and increasing its resistance. The conductor's final electrical resistance serves as a locked physical diary, recording the precise amount of current that passed through the house that month. Back at the macro level, this chemical diary provided the commercial data the early electrical industry required. By measuring the final resistance of the chemical conductor at the end of the month, an engineer could determine exactly how much power a customer had used. This mechanism served as the critical cash register that allowed the massive electrical grid to become a billable commercial enterprise. Tesla used electricity to drive a chemical change, and then used that resulting chemical change to calculate the electricity. While the public was often captivated by massive sparking towers, these silent, invisible reactions were the mechanisms that turned an experimental science into a functional, everyday utility. In 1893, the World's Columbian Exposition illuminated its grounds using alternating current, cementing a highly visible public victory for AC power on a global stage. Supplying the unprecedented energy for this exhibition required rows of massive, iron-heavy rotary machines housed deep within Machinery Hall. The basic architecture of these machines was straightforward: heavy iron armatures spinning continuously within fixed magnetic fields to produce a standard frequency alternating current. While these machines successfully conquered the demands of standard commercial power, laboratory research into advanced lighting and radiant matter required current at exponentially higher frequencies. To meet these new requirements, the baseline engineering assumption of the era was to take the existing rotary generators and spin their armatures at significantly higher revolutions per minute. However, the precise structural traits that made these massive iron machines so effective at the World's Fair rendered them incapable of surviving the physical demands of high-frequency power generation. Pushing a standard iron core armature to extreme rotational speeds triggers a catastrophic breakdown in efficiency. When magnetic polarity rapidly reverses inside an iron core, it encounters magnetic hysteresis, internal friction caused by iron resisting changes to its magnetic state. Simultaneously, it generates eddy currents, localized electrical loops that swirl wastefully within the iron block itself. At extreme speeds, the machine stops converting mechanical energy into electrical output. Internal resistance climbs so high that kinetic energy translates almost entirely into heat. If pushed to the exact frequencies Nikola Tesla required for his advanced lighting experiments, the standard rotary generator stops functioning as a prime mover and instead acts as a highly efficient furnace. Brute forcing a standard rotary machine to achieve high frequencies is physically impossible. The material limits of iron create an absolute thermal roadblock. Tesla's initial theoretical fix to the heat problem was subtractive. He proposed removing the iron core from the rotating armature entirely. By utilizing a purely copper or air core armature, the rotating element could spin through the magnetic field without the dense iron mass generating hysteresis or eddy currents. This diagram illustrates the fatal flaw in that redesign. Without the dense iron mass acting as a conductor to concentrate the magnetic lines of force, the magnetic field dissipates. Consequently, the electrical output of this ironless machine plummets to near zero. Tesla framed this strict engineering deadlock as navigating between two mythical hazards, Scylla and Charybdis. Keep the iron core to maintain magnetic efficiency, and the machine burns itself up from hysteresis. That is the Scylla. Remove the iron to stop the heat, and the magnetic field scatters, producing no usable power. That is the Charybdis. Any electrical generator relying on a rapidly rotating magnetic field is permanently trapped in this paradox. Recognizing this, Tesla abandoned the rotating armature altogether. Tesla realized the true bottleneck was not the materials being used, but the continuous 360-degree rotational motion itself. He proposed a conceptual alternative to the spinning dynamo, linear oscillation. This animation compares the two motions. Instead of an armature spinning on an axis, a mechanical oscillator operates like a piston, moving back and forth in a straight line. This linear movement can be strictly tuned to a specific natural resonant frequency, much like a tuning fork vibrating at an exact pitch. A rotary machine relies on forced, brute strength mechanical RPM. An oscillator utilizes a frictionless, natural rhythm. By placing an electrical coil directly onto this high-speed linear piston, Tesla could pass the wire through a magnetic field, completely bypassing the need for a massive rotating iron core. By changing the geometry of motion from a circle to a line, Tesla achieved extreme mechanical speeds without triggering the thermal penalties of iron. This concept materialized as Tesla's mechanical and electrical oscillator, featuring a highly precise physical architecture. The prime mover is pneumatic. It consists of a precision metallic piston driven rapidly back and forth along a track by compressed fluid or steam. The electrical wire coil is physically coupled directly to this rapidly vibrating piston. Instead of spinning, the coil rapidly oscillates into and out of a stationary, constant magnetic field. Because the magnetic field itself is no longer rapidly rotating through a dense iron block, the extreme heating from hysteresis and eddy currents is entirely avoided. This side-by-side animation shows how the frequency of the electrical output is mathematically locked to the mechanical stroke rate of the piston. This yields extreme efficiency gains. The device transfers mechanical energy to electrical energy directly, without the drag of heavy rotary bearings. This architecture also eliminates the need for commutators, the complex mechanical switches used in standard dynamos to reverse current direction, which generate significant friction at high speeds. Most importantly, mechanical resonance ensures the electrical frequency remains absolutely constant. This exact stability was a strict requirement for Tesla's lighting experiments. This mechanical engine obeyed the laws of electrical resonance, solving the Scylla and Charybdis deadlock. The immediate laboratory output of the oscillator's output was powering high-potential vacuum tubes and advanced lighting systems. The precise, unvarying high-frequency current allowed Tesla to excite phosphorescent bulbs highly economically. Standard high-speed rotary machines produced variable currents that caused the gas inside early arc lamps to rapidly heat and cool, emitting a loud, shrill noise. The oscillator's flawless output operated in total silence. The sheer stability of this oscillator became the reliable foundation for his deeper investigations into radiant matter and high-frequency phenomena. The mechanical oscillator effectively served as the ultimate prime mover for his most famous high-voltage electrical coils. While history heavily documents Tesla's electrical coils and glowing tubes, it frequently omits the mechanical engine required to drive them. Achieving the seemingly magical future of wireless electricity required mastering advanced pneumatics and mechanical resonance first. The iron rotary core presented a trap, a choice between destructive heat or non-existent power. Standard engineering addresses this by compromising between heat and efficiency, accepting a flawed, inefficient middle ground to keep the rotary machine functioning. Tesla's engineering philosophy dictated a different approach. When the structural logic of a system is flawed, abandon it completely rather than optimizing a broken engine. The mechanical and electrical oscillator bypassed the compromise entirely by inventing a wholly new category of machine based on linear motion. True engineering breakthroughs rarely come from forcing old architectures to work harder. They emerge from reimagining the physical geometry of the problem itself. When engineers first flipped the switch on alternating current arc lamps, the lights illuminated the room, but they also emitted a deafening scream. Every time a lamp sparked to life, a harsh, relentless hum made indoor use nearly impossible. The immediate assumption was mechanical. Engineers suspected the metal housing or the carbon rods themselves were vibrating against each other, but tightening the fixtures did nothing to stop the noise. The sound was actually coming from the empty space between the electrodes, the volume of gaseous matter trapped directly inside the electrical arc. Alternating current, by definition, pulses. As this pulsating electrical energy passes through the gas, it acts as an extreme, rapid-fire heat source. When the alternating current wave hits its maximum peak, it violently heats the gas, forcing the molecules to rapidly expand outward. Then, as the current drops to the zero crossing, the exact trough of the wave, the energy cuts out for a fraction of a second, allowing the gas to instantly cool and contract. This continuous expansion and contraction acts like a pneumatic piston. The gas physically pumps against the surrounding atmospheric air. Every electrical pulsation translates directly into a mechanical motion. As the sine wave peaks, the gas expands, pushing out acoustic sound waves. The pitch of that hum is tied to the frequency of the alternating current. A standard low-frequency current produces a highly audible drone. The noise is a direct thermodynamic translation of low-frequency power. To silence the light, the electrical frequency must be accelerated so high that the resulting sound waves push past the limits of human hearing. The objective was to push the generator's alternating current frequency above 20,000 cycles per second, rendering the arc lamp silent to the human ear. Nikola Tesla took on this challenge. His goal was to achieve these high frequencies through rigorous, iterative mechanical engineering. To understand the difficulty, we have to look at how a standard 19th century dynamo works. You have a central conductor, called an armature, rotating rapidly past a series of stationary magnetic poles, called a stator. These dynamos were massive, heavy iron behemoths. Crucially, their entire physical architecture was built for very low frequencies, usually around 60 cycles per second. Mechanically, to increase that frequency, you only have two variables to adjust. First, you can increase the raw rotational speed of the central armature. Second, you can multiply the total number of magnetic poles placed around the outside of the stator. More poles passed per rotation equals more alternating cycles. The mathematical formula for achieving high frequency is simple, but forcing these giant iron machines to physically execute it introduces a catastrophic material limit. The failure point lies at the very center of the generator's operation, the solid iron core of the spinning armature. Iron is necessary to channel magnetic flux, the flow of magnetic energy between the generator's poles, and concentrate it through the conductor. For high frequencies, we spin the iron core past dozens of poles at extreme speed. At the molecular level, passing a north pole snaps the magnetic domains into alignment. Hitting a south pole milliseconds later, every domain violently reverses direction. This mechanical reality introduces the key technical constraint of the system, magnetic hysteresis. Magnetic hysteresis is the internal molecular friction caused by the constant, rapid reversal of magnetic polarity, which manifests physically as heat. As the frequency increases to thousands of cycles, this thermal buildup multiplies exponentially. Pushed to extreme reversal rates, the iron gets so hot that the machine completely ceases to function as an efficient electrical generator. The mechanical energy of the spinning shaft is no longer being converted into electricity. It is instead being cannibalized by the iron and converted into catastrophic melting heat. Faced with a melting core, the immediate engineering countermove is to remove the iron from the armature entirely. By removing the iron core, we leave only copper windings. The machine stays cool, but an immediate failure follows. Without solid iron to focus the forces, magnetic flux scatters loosely. The induced electrical current plummets to zero, rendering the machine useless. Tesla documented this exact trap in his notes, referring to it as his Scylla and Charybdis dilemma, a reference to the mythological hazard of navigating a narrow strait between two equal dangers. Path A is Scylla: keep the iron core to maintain strong magnetic induction, but ultimately melt the machine from hysteresis heating. Path B is Charybdis: remove the iron to keep the machine cold, but generate absolutely no usable electrical power. The ferromagnetic properties of iron make traditional rotating generators a technological dead end. They are physically incapable of scaling to the high frequencies required. How do you generate high frequencies if rotating magnetic fields through iron is physically unscalable? Inside his laboratory, Tesla systematically tested standard rotary dynamos. He pushed them to thermal breaking points, analyzed mechanical failures, and ultimately discarded them. Tesla identified the failure point, the assumption that a generator must rotate in a continuous circle. He isolated the specific motion causing the thermal loss. The heavy armature was constantly being dragged in circles through alternating north and south magnetic fields, cooking the iron from the inside out. This led to a radically different concept. What if the conductor didn't rotate at all, but instead vibrated back and forth in a straight line? To bypass the thermal bottleneck of iron, Tesla abandoned the rotating architecture that had defined the entire electrical industry up to that point. His mechanical solution was a completely new class of machine, the mechanical and electrical oscillator. The surviving hardware reveals a design relying entirely on a linear, reciprocating brass mechanism rather than a circular rotor. The design eliminates the massive, heavy, rotating iron armature structure that caused the thermal failures in previous generations. By utilizing a high-speed linear oscillation, vibrating the conductive components back and forth inside a stable magnetic field, the machine achieved the extreme rates of movement required for high frequency without triggering hysteresis losses. This singular invention successfully navigated the Scylla and Charybdis paradox, maintaining electrical output while completely avoiding thermal destruction. This breakthrough solved the initial problem. The oscillator generated frequencies so high that the glowing gas of an arc lamp expanded and contracted in silence. Tesla achieved high-frequency power by methodically dismantling and then physically bypassing the thermodynamic limits inherent to 19th century materials. Generating continuous rotation in early electric motors required a constant reversal of magnetic polarity to keep the rotor in motion. Engineers achieved this using mechanical commutators, which functioned as physical switches, literally breaking and reconnecting the circuit to flip the direction of the current. But this mechanical switching created immediate physical limits. The metallic brushes caused high friction, generated severe heat, and produced constant sparking, factors that strictly limited the voltage these motors could safely handle. These commutator issues created a massive bottleneck. They prevented electric motors from scaling up for heavy industrial tasks or operating on high-voltage power lines. Unlocking the potential of electrical power required an entirely different approach, one that eliminated the mechanical switch. In May 1888, Nikola Tesla presented a paper to the American Institute of Electrical Engineers that detailed a radical solution. Tesla boldly proposed discarding the commutator entirely. He aimed to create a magnetic field that rotates electrically, using no moving parts at all. To achieve this, he used polyphase alternating currents. A polyphase system uses multiple independent AC currents that are staggered in time to provide a continuous flow of energy. His early prototypes relied on stationary coils and lacked brushes entirely. This move shifted the challenge of rotation away from mechanical engineering and into the realm of trigonometric vector calculations. We model this using a single alternating current driving a pair of stator coils. As the sine wave moves towards its positive peak, the magnetic vector in the center grows straight up, reaching maximum strength at the top. When the wave crosses the zero axis and hits its negative trough, the vector shrinks to zero, flips, and grows straight down towards the south. Driven by a single phase, this magnetic field only pulses back and forth along a vertical axis. This leads to the dead center problem. A rotor placed in this pulsing field gets stuck in alignment, unable to initiate rotation on its own. A single phase provides a push-pull force, but it lacks the lateral geometric component necessary to move a rotor in a circle. To fix this, Tesla added a second pair of coils, placed exactly 90 degrees perpendicular to the first. He drove these horizontal coils with a second AC wave, phase B. Crucially, phase B is offset in time by exactly 90 degrees, 1/4 of a cycle from phase A. This allows for vector summation, the process of adding the magnitude and direction of multiple vectors to find their combined result. In this motor, the total magnetic field at any moment is the resultant vector of phase A and phase B. This combination of physical perpendicularity and electrical phase shifting provides the geometric coordinates for continuous rotation. At the start of the cycle, t equals 0, phase A is at its absolute maximum, while phase B is at 0. With phase B at 0, the resultant vector points straight north, driven entirely by phase A. 1/8 of a cycle later, phase A decreases in strength, while phase B increases. Both sets of coils generate equal orthogonal magnetic fields. The vector sum of these two fields creates a resultant vector that has rotated exactly 45 degrees. At the 1/4 cycle mark, phase A has hit 0 and phase B has reached its maximum. The magnetic pole has shifted 1/4 of the circumference, with the resultant vector now pointing straight east. Playing the timeline forward reveals the continuous path of the resultant vector. The vector maintains a constant magnitude as it rotates, never pulsing or flipping like the single-phase model. Continuous mechanical rotation has been achieved through the intersecting arithmetic of electrical waves. To capture this energy and turn it into mechanical work, we introduce a closed conducting cylinder called the rotor. We place this rotor into the rotating magnetic field, triggering Faraday's law of induction. As the magnetic flux lines sweep in a circle, they cut through the stationary copper, inducing electrical currents within the solid metal of the rotor. These induced currents then generate an opposing magnetic field within the rotor itself. The rotor's magnetic field attempts to lock onto the spinning stator field. This creates torque, dragging the cylinder into a spin. The induction motor works by having the magnetic field pull the rotor, achieving high-speed motion with no physical electrical connection to the moving parts. This brushless design eliminates the friction and sparking found in the original DC motor designs. This elegant mathematical concept allows for heavy, robust industrial construction. Removing the mechanical commutator allowed motors to run at the high voltages required for large-scale power grids. This polyphase vector logic provides the foundation for industrial power, from pumping city water to moving electric trains and running automated factories. Ultimately, Tesla's great achievement was making the alternating grid itself perform the switching, turning mathematical waves into mechanical power. Alternating current motors rely on a specific physical phenomenon to generate motion, the rotating magnetic field. Instead of relying on mechanical contact, they use invisible forces pulling in a continuous circle. To create this continuous circular pull, the motor requires two or more distinct electrical currents. Crucially, these currents must be out of phase, peaking at slightly different times to pull the rotor in a sequence. Nikola Tesla engineered a motor that perfectly utilized these multi-phase currents. His early design successfully generated this rotating magnetic attraction, eliminating the need for brushes or commutators. But this early motor had a strict requirement. It needed a specialized polyphase generator, like this heavy, dedicated dynamo, to supply those distinct, perfectly timed currents. The system required a continuous, unbroken electrical path, carrying multiple distinct phases directly from the generator down the line into the motor's stator coils. While highly efficient, this polyphase motor existed in a closed ecosystem. It was dependent on a specialized power source that did not exist in the broader world. Outside the laboratory, the actual electrical distribution networks installed across cities in the 1890s looked very different. These existing systems were single circuit. They provided only one continuous phase of alternating current to their consumers. Ripping out millions of dollars of installed two-wire transmission lines to accommodate the new multi-phase requirements was economically impossible for utility companies. This diagram shows the physical wiring conflict. A polyphase setup required 3 wires to carry offset currents, but standard single-phase grids only had 2. When a multi-phase motor is plugged into a single-phase line, the secondary phase disappears. The motor receives only one alternating wave. Without that secondary offset wave to pull the magnetic field forward, the motor stops rotating entirely. Widespread AC adoption stalled on a hard incompatibility. The motor's design required a multi-phase feed that the existing single-circuit grid simply could not provide. To understand why a single alternating current fails to produce motion, we have to look at the exact physics inside the stator. Here, a single AC wave enters a coil, producing a magnetic field that only oscillates along a stationary axis. Mathematically, this pulsating magnetic field moves strictly back and forth rather than rotating. Now, we place a stationary rotor into this pulsing environment. As the AC wave alternates from positive to negative, the magnetic vector pulls the rotor equally in exact opposite directions. The result is zero rotational torque. The rotor is locked in a balanced tug-of-war. Breaking this deadlock requires a second sine wave. This out-of-phase current shifts the magnetic vector perpendicularly as the first weakens. This rotating vector is the prerequisite for initiating rotation. If a rotor is already manually spun up to speed, its momentum can catch and lock into the single-phase frequency, keeping it in motion. In industrial applications, manual starting is useless. A motor must be able to self-start while attached to heavy physical loads. Overcoming the zero starting torque deadlock of single-phase power was the definitive hurdle for commercializing AC motors. Without a solution to this vector problem, machines like this early alternating current motor would remain inert on the workbench. Alternating current power would be restricted strictly to large industrial plants that could afford to build and run dedicated polyphase generators. For alternating current to reach small businesses and residential grids, the motor had to adapt to the existing wires, rather than waiting for the wires to adapt to the motor. The physics of a single AC wire are fixed. Therefore, the internal architecture of the motor itself had to be redesigned. Tesla detailed his engineering pivot in his writings, specifically noting the necessity of utilizing his motors in connection with ordinary systems of distribution. He abandoned the attempt to change the external grid. Instead, he forced the motor to simulate the multi-phase conditions it lacked. The engineering objective was clear. The motor must take a single input circuit and split it internally. This diagram shows a single incoming sine wave hitting a node. By splitting the path and artificially delaying one portion of the wave, it creates a secondary offset wave. This internal phase splitting finally provides the secondary vector needed to initiate the rotating resultant attraction inside the stator. This exact mechanism birthed an entirely new class of machine, the self-starting single-phase motor. Tesla engineered an entire library of methods to split the phase, relying on different electrical properties to force the delay. The first method utilized circuits of differing resistance. This schematic of a split-phase stator shows the single current routed through two parallel coils. One is thin, creating high resistance. The other is thick, creating high inductance. This physical difference forces the current in one coil to peak later than the other. The second method introduced artificial magnetic lag directly into the iron core. By shielding specific portions of the iron core, the motor physically delays the magnetization in those areas of the stator, mimicking an out-of-phase current. The third method involved introducing condensers, or capacitors, into the armature or field circuits. A capacitor is a component that stores and releases electrical energy, creating a timing shift in alternating current circuits. A capacitor alters the phase angle of the current, actively pushing it out of sync with the primary single-phase line. Whether utilizing resistance, magnetic shielding, or capacitance, Tesla engineered the motor to bootstrap its own rotating magnetic field entirely from a single wire. This diagram shows the shift from rigid hardware constraints to system flexibility. On the left, a polyphase generator is strictly tied to a polyphase motor. On the right, a standard single-phase generator connects to the modified single-circuit motor. By managing the phase differential internally, the motor was permanently decoupled from the strict requirements of its power source. Alternating current motors could immediately plug into and operate on the vast pre-existing single-phase lighting grids already crisscrossing cities. The single-circuit motor served as the bridge between theoretical electrodynamics and practical, scalable grid engineering. Inventing perfect technology in a vacuum is only half the equation. Achieving scale requires designing the imperfect installed infrastructure of the real world. These internal phase-splitting methods provided the necessary architecture to scale the 20th century electrical grid, bridging the gap between laboratory motor prototypes and installed urban power lines. In the late 1880s, electrical power expansion hit a mechanical wall. At the center of every direct current motor sat a mechanical commutator. To maintain rotation in a DC motor, the internal current must constantly reverse its direction. The commutator acts as a physical switch, a rotating cylinder made of metal segments and stationary brushes, to manually break and reconnect the circuit hundreds of times a minute. This reliance on constant physical contact creates rapid degradation. Friction grinds down the metal brushes, and at high voltages, the small gaps between segments trigger destructive electrical arcs. Scaling up industrial electricity meant building larger, heavier machines, but increasing the voltage through mechanical commutators guaranteed catastrophic failure. Nikola Tesla looked past the need for a tougher physical switch. He began treating the problem as one of vector mathematics and spatial geometry. Tesla proposed a system that could eliminate mechanical current reversal entirely. Removing the commutator meant decoupling mechanical wear from electrical generation. This transition was the only path toward creating industrial motors that could operate at massive scales without breaking down. This schematic illustrates the architecture Tesla outlined in his early technical records. It features a stationary outer ring of coils, the stator, and an internal spinning rotor, separated by an empty air gap. Tesla's design utilized alternating current, or AC. Unlike direct current, which flows in one direction, AC oscillates back and forth in a continuous wave. Standard AC systems of the time were single-phase, transmitting a single oscillating wave. This current pushes and pulls, but it lacks the spatial characteristics required to move a rotor in a continuous circle. The solution required a polyphase system. Polyphase refers to configuration that uses multiple independent alternating currents with their wave cycles intentionally offset in time. Tesla hypothesized that by feeding these offset currents into a specific arrangement of stationary coils, he could synthesize a continuously rotating magnetic field. The physical coils of the stator never move. Instead, an invisible magnetic field sweeps around the inner circumference, reaching across the air gap to drive the internal armature. Tesla's thesis moved the challenge of rotary motion out of the realm of mechanical engineering and into the realm of spatial geometry. To understand the math, we start with a single pair of vertical electromagnetic coils. This setup generates a single magnetic field vector. As the alternating current flows in the positive direction and peaks, the magnetic field reaches its maximum upward strength. When the AC wave drops back down and crosses the 0 point, the current stops and the magnetic field vanishes. The rotor simply vibrates in place, locked on a single axis. A one-dimensional oscillating field is mathematically insufficient for rotation. To create torque, the system requires a more complex spatial arrangement of coils. The solution is a two-phase system. We add a second alternating current, offset by exactly 90 degrees. This requires a second pair of electromagnetic coils on the stator, positioned 90 degrees away from the first. The first wave powers the vertical coils, and the offset wave powers the horizontal coils. Both pairs pulse along their respective axes, completely out of phase with each other. Pause at time 0. The vertical flux is at maximum. Horizontal is 0. The vector sun points straight up. Advancing 45 degrees, the vertical weakens as the horizontal grows. The combined force points diagonally. At 90 degrees, the vertical hits 0. The horizontal is at maximum, shifting the vector right. Unpaused, the resultant magnetic vector never drops to 0. Instead, the offset oscillations combine to trace a continuous 360-degree circle. While the physical coils remain bolted in place, Tesla generated continuous rotation through offset oscillations. To capture this motion, Tesla used a closed-loop armature, called a squirrel cage rotor. It consists of an iron core wrapped in heavy copper loops. This rotor has no wires connecting it to the external power supply. It is physically isolated from the rest of the machine. As the stator's magnetic vector sweeps through the space occupied by those copper loops, it triggers Faraday's law of induction. A changing magnetic field induces an electrical current in a nearby conductor. As the stator's invisible flux cuts across the copper, it induces a massive current directly inside the rotor's closed loops. This induced current then triggers Lenz's law, which dictates that an induced current generates its own magnetic field. The rotor becomes an electromagnet, generating its own magnetic vectors in response to the stator. This creates what Tesla called resultant attraction. The newly formed magnetic poles on the rotor attempt to lock into alignment with the rotating poles. Because the stator's field never stops moving, the rotor is continuously dragged in circles, chasing an invisible magnetic wave to generate contactless mechanical torque. The resulting motor is an incredibly durable and efficient system. The mechanical commutator and physical brushes, the primary points of failure in DC motors, are completely eliminated. Without brushes, there is no friction to wear down parts, and no sparks to cause fires. These motors can operate continuously at the massive voltages required for heavy industry. This breakthrough made alternating current the practical choice for power distribution. It was the centerpiece of the 1893 Columbian Exposition, effectively ending the War of the Currents. Today, these principles run factory lines, municipal water pumps, and the drivetrains of electric vehicles. Tesla's polyphase motor replaced physical mechanical contact with the geometry of invisible fields. Over a century after its invention, this induction method remains the global standard for high-voltage power conversion. In the early 1890s, Nikola Tesla began investigating the strict limitations of standard alternating current distribution systems. The core objective of standard transformer design is maximizing magnetic coupling. The goal is to ensure that 100% of the magnetic flux generated by the primary coil links directly to the secondary coil. Tesla observed that in these ordinary transformer types, the wave of electromotive force, or EMF, the electrical action acting as the voltage driving this drivetract, of the secondary coil very nearly coincides with the primary, just with the opposite sign. This tight coupling posed a severe problem for the era's most volatile grid lamps, series arc lighting. These lamps relied on a raw plasma arc struck between two carbon rods, and they exhibited negative resistance. Negative resistance means that as the arc's temperature increases, its electrical resistance drops. Supplying a negative resistance load with a constant voltage is destructive. As the carbon arc heats up and resistance falls, the current spikes uncontrollably, driving the system straight into thermal runaway. To operate these highly volatile grid loads safely, engineers needed a constant current source. Achieving that required deliberately breaking the golden rule of perfect magnetic coupling. Tesla's solution was a physical intervention in the transformer's geometry. He placed a thick block of iron directly in the space between the primary and secondary coils. This structural change intentionally degrades the mutual inductance of the system. It places a barrier with high magnetic reluctance, a measure of opposition to the magnetic flux, right in the middle of the core. Tesla referred to this component as a magnetic shield. However, in strict mechanical terms, this central piece of iron operates as a magnetic shunt. A magnetic shunt provides an alternative, bypass path for magnetic flux to travel. Instead of forcing all the flux through the secondary coil, the shunt deliberately creates magnetic leakage. Tesla is not attempting to block the magnetic field entirely. By engineering a productive leak, he is introducing a passive mechanism to control the flow of electrical energy. Under stable conditions, the primary coil generates an alternating magnetic flux. Because of the divided core geometry, this flux splits. A small percentage bleeds into the central iron shunt, while the vast majority links with the secondary coil. The majority of the flux successfully reaches the secondary coil because under normal load resistance, the secondary circuit's internal impedance is low enough to permit the magnetic linkage. In this stable state, the shunt sits mostly idle. It draws only a baseline level of leakage flux, keeping the transformer calibrated to deliver the working voltage required by the arc lamp. During nominal operation, the system mimics a standard transformer. The crucial difference is the presence of this passive pressure relief valve, waiting for a specific trigger. That trigger occurs when the arc lamp load suddenly drops to near zero resistance. This failure state demands a massive, immediate influx of electrical current. This forces Lenz's law into effect. As current spikes, the secondary coil generates an immense opposing magnetomotive force. This acts like a magnetic wall, pushing back the incoming primary flux. Bypassing the secondary coil entirely, the flux heavily routes through the central magnetic shield. The secondary coil weaponizes its own back EMF to choke off its power supply. The shield security routes the excess magnetic energy away from the load. Faraday's law of induction dictates that the voltage induced in a circuit is directly proportional to the rate of change of magnetic flux linking it. Because the primary flux is now bypassing the secondary coil, the flux linkage drops drastically. With fewer magnetic flux lines cutting across the secondary wires, proportionally less electromotive force is induced in the circuit. This effect occurs instantaneously. The voltage drops exactly in proportion to the load's tendency to draw more current, all without a single moving mechanical part. Returning to Tesla's observation, this specific physical geometry forces the EMF waves of the primary and secondary coils out of coincidence, completely decoupling their phases. The iron shield serves as a solid-state, zero-latency feedback loop that dynamically throttles electrical transfer based strictly on real-time load demand. This chart shows an ideal transformer's electrical behavior. Voltage remains a flat horizontal line as current increases, extending infinitely until burnout. On the right, we plot Tesla's shielded transformer. The line begins horizontally, but as current rises, it takes a steep vertical drop downward. That vertical drop maps the exact moment the current hits the physical threshold dictated by the shield's geometry. The voltage plummets to keep the current rigidly constant. A purely passive geometric modification to the iron core completely rewrites the mathematical output profile of the machine. The engineering victory is the achievement of perfect current regulation without adding active, heat-generating resistive components that waste system power. The design utilizes the inherent instability of the load, specifically its back EMF spikes, as the exact mechanism to trigger its own regulation. This proves that in alternating current systems, ultimate efficiency is not universally achieved by maximizing magnetic coupling or eliminating leakage. True mastery of alternating current lies in designing magnetic geometries that dictate the phase and flow of energy. Tesla arranged the iron and copper so that the laws of physics do the engineering work for you.
By the early 1890s, the power industry faced a severe engineering bottleneck. As laboratories aggressively pushed for higher and higher voltages, their alternating current generators failed to maintain a mathematically stable frequency. The mechanical architecture of the era relied on rotary dynamos. These heavy units were physically driven by steam engines, connected through complex, lossy systems of leather belts and interlocking gears. This chain of moving parts introduced severe variables. Fluctuations in boiler steam pressure directly and unpredictably altered the rotational speed of the driving engine. Engineers call this resulting instability frequency drift. Frequency drift is the continuous, erratic deviation of an alternating current's waveform period from its intended target rate. This animated schematic illustrates a second variable of instability, electrical load. Applying or removing an external electrical load creates sudden mechanical drag on the armature, further disrupting the rotational speed and heavily distorting the AC sine wave in real time. Without a perfectly constant period AC waveform, precision scientific investigation and advanced high-frequency power transmission were mathematically impossible. The signals would simply degrade. The mechanical degrees of freedom inherent in 19th century rotary systems, the slipping belts, the grinding gears, and the variable steam, were incompatible with the precision required to advance electrical engineering. When rotary dynamos failed to hold high frequencies, researchers turned to an alternative method, the spark gap. A spark gap is an apparatus that forces a high-voltage electrical discharge to jump across a physical break in a circuit, a process used to induce rapid, high-frequency oscillations. This data visualization compares the two outputs, exposing the fatal flaw of the spark gap. While it produces high frequencies, the resulting electrical output is inherently erratic, filled with noise, and rapidly decays after every discharge. Because the spark gap produced such inconsistent energy, laboratories could not standardize their high-frequency experiments. The results from one test could not be reliably replicated in another. A solution arrived in August 1893 when Nikola Tesla delivered a lecture to the Electrical Congress at the Chicago World's Fair. The Electrical Congress was an international gathering of the world's leading electrical engineers, convened to establish industry standards. Tesla presented an ambitious thesis. He had engineered a machine capable of generating perfectly constant period AC, entirely independent of supply pressure and frictional losses, without utilizing a single spark gap. To achieve this theoretical ideal, Tesla abandoned rotary motion. He aimed to reinvent the physical relationship between the prime mover and the electrical generator. The first half of Tesla's 1893 solution was a constant period mechanical reciprocator that eliminated wheels, belts, and rotary gears. This CAD-style cross-section details the pneumatic cylinder, C. A heavy piston, P, fits tightly inside. Pressurized fluid enters through specialized channel ports, O. As the piston passes the central exhaust port, I, it vents the fluid, creating a differential that automatically snaps the piston back. This precise, automated reciprocation achieves a state called isochronism. Isochronism is a mechanical state where the frequency of a system's oscillation remains strictly independent of the force driving it. Because the physical distance between the machined ports dictate the exact stroke length of the piston, the oscillation is locked into a constant frequency, regardless of how much steam pressure is applied. Furthermore, the piston is cushioned by pockets of air at each end of its stroke. This air spring effect minimizes frictional losses against the cylinder walls, bypassing the heavy wear of rotating crankshafts. By utilizing fixed port geometry instead of rotary linkages, Tesla engineered a prime mover whose oscillation period was mathematically immune to variations in supply pressure or internal friction. But mechanical reciprocation was only half the problem. Tesla still had to convert this timed physical movement into a usable, high-frequency electrical current. Tesla unified these systems by constructing the reciprocating iron piston P to function simultaneously as the magnetic armature core. As it is driven back and forth, it plunges through the surrounding electromagnetic coils, rapidly cutting magnetic flux lines and generating alternating current. There are no commutators, no brushes, and no intermediate mechanical linkages. The physical linear motion generates the electrical current directly. This architecture solves the issue of variable electrical loads. The electrical frequency is now locked in a 1-to-1 physical ratio with the stabilized pneumatic frequency of the piston. The system entirely bypasses the limitations of standard high-frequency generators. It experiences no mechanical overheating from belt friction and suffers zero spark gap signal degradation. To adjust the output frequency for different experiments, a technician simply altered the mechanical weight of the iron piston or machined a cylinder with different port dimensions. Tesla termed this architecture a unified prime mover. A unified prime mover is an engineering design that physically merges the power-generating engine and the electrical generator into a single continuous reciprocating component. By making the engine and the generator the exact same moving part, Tesla bypassed the mechanical drift that caused frequency instability in the 19th century. At the Electrical Congress in Chicago, Tesla submitted this architecture to rigorous empirical testing. The assembled apparatus was surprisingly compact. Sitting on a laboratory table, the robust oscillator was connected directly to a standard air compressor. Tesla applied extreme testing conditions. He drastically altered the input air pressure from the compressor, actively attempting to force the mechanical frequency to drift. Next, he tested the electrical load. He rapidly switched heavy electrical loads on and off the circuit, purposely introducing massive variable drag on the armature. This simulation charts the definitive result. Despite the massive external variances in pneumatic pressure and electrical load, the output remained a perfectly stable, constant period sine wave. This performance provided researchers with a precision clockwork for alternating current that had never existed before. The Chicago demonstration provided empirical proof that perfect isochronism could be engineered directly into the foundational hardware of a generator. The immediate historical impact of the oscillator was practical. It provided the scientific community with its first truly reliable source of high-frequency, high-potential alternating current. Supplied with this stabilized power, laboratories could conduct repeatable, verifiable experiments in artificial illumination and wireless energy transmission. Popular culture associates Tesla's high-frequency work exclusively with the erratic spark gaps of his resonant coils.
In reality, his preferred engineering paradigm for precision research relied on this mechanical solution. The oscillator's design principles anticipated modern control theory, demonstrating how to isolate and reduce mechanical noise in delicate scientific instruments. Complex systemic instability is not always corrected with additional mechanisms. Often, it requires the total unification of the system's core components. The oscillator proves that electrical stability begins with the ruthless elimination of mechanical degrees of freedom. In his pursuit of perfect isochronism, Tesla looked past the incremental improvement of existing generators to redefine the absolute mechanical boundaries of electrical engineering.
To generate starting torque, an alternating current induction motor requires a rotating magnetic field. It needs magnetic flux lines moving in a continuous, perfect circle to pull the internal rotor along and force it to spin. Early engineers achieved this rotation by utilizing polyphase power. Polyphase power is an electrical distribution method that transmits multiple independent electrical currents, each slightly offset in time, to sequentially energize the motor's poles. But this creates a severe infrastructure constraint. Delivering polyphase power requires complex multi-wire distribution lines. Throughout the late 19th century and across most modern residential grids today, the electrical infrastructure is restricted to a single-phase, two-wire circuit. A single alternating current cannot rotate. It is a solitary wave that only creates a pulsating magnetic field, pushing and pulling in a straight, linear direction as the current reverses. Because a single wave only pushes back and forth, it generates zero starting torque. A motor connected to a single-phase grid remains completely paralyzed at startup. Overcoming this physical roadblock was essential for the widespread adoption of alternating current. Nikola Tesla addressed this specific grid limitation by turning his attention to the internal architecture of the motor itself. In Chapter X of his collected writings, Tesla detailed a solution he called a motor with a current lag artificially secured. This introduced a strict engineering paradox. You need two distinct out-of-phase magnetic forces to create rotation, but the utility line only provides a single, uniform oscillating wave. His answer was to design a phase splitter. A phase splitter is a circuit configuration that divides one incoming electrical path into two branches and manipulates the timing of the electricity flowing through them internally. Tesla's objective was to build a machine that accepts a standard, single-phase input from the wall, but simulates the timing of a complex polyphase system entirely inside its own housing. He realized the solution to a mechanical lack of rotation was not a physical mechanism attached to the rotor. The solution required manipulating the electrical properties of the copper circuits themselves. To understand how this works, we have to look at impedance. Impedance is the total measure of how an alternating current circuit resists the flow of electricity. Impedance consists of two distinct components. The first is standard electrical resistance, which acts like physical friction. The second is inductive reactance, which acts as a resistance to any change in the flow of the current. This graph maps an alternating current moving through a purely resistive wire. You can see the current wave and the voltage wave are perfectly in phase. They rise and fall in perfect unison. Now observe what happens when we replace that straight wire with a tightly coiled wire. The coil generates self-induction, which actively fights the alternating flow. The current wave physically shifts to the right on the timeline, lagging behind the voltage. This establishes a rigid physical rule. In a highly inductive circuit, voltage leads current, resulting in a measurable temporal delay. By deliberately routing electricity through different physical wire geometries, an engineer can decouple the timing of the current from the timing of the voltage. When a single AC line reaches a parallel junction, the current divides, traveling down both branches simultaneously. This schematic illustrates Tesla's design from Chapter X. A single alternating current enters from the grid and splits into two parallel paths, each leading to a different set of electromagnetic coils. Path A is wound into a large coil to maximize self-inductance. As we just established, this geometry actively slows the current down, pushing it out of phase with the incoming voltage. Path B is wired in series with a resistor. This maximizes standard electrical friction while keeping inductance low, meaning the current wave passes through unimpeded by any time delay.
Look at the outputs mapped together. The current flowing out of path A is now physically out of sync with the current flowing out of path B. Tesla successfully manufactured two distinct offset electrical waves from a single incoming source, purely by altering the topology of the circuit. Having secured the time delay, the next step is applying those offset currents to the physical geometry of the motor. This top-down cross-section shows the stator architecture for the Chapter X motor. It features 4 electromagnetic poles arranged in a continuous circle. The coils connected to the highly inductive path A are positioned at the top and bottom vertical poles. They receive the delayed current, pulsing late in the cycle. The coils connected to the standard resistive path B are placed at the left and right horizontal poles, positioned exactly 90 degrees away from the first set. At time 0, the resistive horizontal coils receive their current peak, exerting maximum magnetic strength. At this exact moment, the delayed current in the vertical coils is still climbing, leaving them magnetically weak. A fraction of a second later, the delayed inductive current finally reaches its peak. The maximum magnetic strength physically shifts 90 degrees to the vertical poles, while the horizontal poles fade. Watch the bold arrow in this diagram. This is the resultant vector, the combined sum of the magnetic fields. As the two offset sine waves rise and fall out of phase with one another, the resultant vector continuously sweeps in a circle. By applying a temporal electrical delay across a 90-degree spatial layout, the stationary iron core generates a true rotating magnetic field. The final mechanical component is a closed-loop metal rotor. Dropping into the center of this spinning resultant vector field, it instantly snaps into motion. As the rotating magnetic field sweeps across the rotor, it physically cuts through the metal, inducing secondary electrical currents deep inside the cylinder. These secondary currents generate their own magnetic forces, which repel against the stator's field. The rotor is physically pushed to chase the spinning field. Looking at the operational machine, all of this continuous rotational energy is being pulled from just 2 incoming single-phase wires. The starting torque is entirely dependent on the electrical asymmetry carefully engineered into the parallel branches of the stator. Generating a rotating field usually requires laying massive distribution cables across miles of terrain. This design contained the solution within inches of copper wire. Tesla's artificial current lag bypassed a major distribution limitation of the 19th century, allowing AC motors to run on the cheap existing 2-wire grid. This engineering logic remains highly relevant. The principle of impedance-based phase splitting is the foundational architecture for most single-phase motors today. It starts the HVAC compressor, spins the washing machine drum, and drives light industrial pumps. Tesla took a dimension of time, a microscopic delay in an electrical wave, and translated it into the dimension of space using copper wire and iron geometry. Chapter X stands as definitive proof that a seemingly insurmountable mechanical limitation can be solved entirely through invisible electrical architecture.
Nikola Tesla approached electrical distribution as a problem of rigorous practical engineering. He focused on bridging the gap between massive power generation and localized industrial application. In the late 19th century, massive alternating current generation halls began pushing electricity across vast distances. But these early grids were almost exclusively single-circuit systems. They delivered only a single phase of alternating current to the homes and factories at the end of the line. While a single AC phase is efficient for lighting a bulb or transmitting power over miles of wire, it lacks the rotational mechanics required to kickstart a heavy industrial motor from a dead stop. For the AC revolution to power the industrial world, engineers needed a way to make those simple single-phase lines operate self-starting rotary machines. To understand the mechanical roadblock, we look inside the stator of a standard early alternating current motor, which relied on a single set of wire coils interacting with that lone incoming electrical phase. When a single AC sine wave reaches its positive peak, it generates a magnetic vector pointing straight up. As the current drops to its negative peak, the pole flips 180 degrees straight down. Halfway between peaks, the current stops, and the field collapses entirely. This continuous back-and-forth flipping creates a pulsating magnetic field. The force pushes and pulls in a straight line, but it never rotates. Unlike a pulsating field, a polyphase system utilizes 2 or more alternating currents offset in time. Polyphase is a configuration that uses multiple AC waves to create a rotating magnetic field through overlapping electrical cycles.
A motor trapped in a single-phase pulsating magnetic field is locked in physical equilibrium. It is pulled equally in opposing directions and remains completely stationary. In Chapter 22 of his compiled writings, Tesla outlined a method to operate a polyphase motor using a standard single-circuit AC power source. First, he divides the incoming wire into two parallel branches, circuit A and B. He arranges their coils orthogonally, 90 degrees apart around the rotor. With equal resistance, flow is perfectly synchronized. Two identical sine waves enter the coils, peaking at the exact same time. Because the currents peak simultaneously, their magnetic poles combine. The result is a single, stronger vector that only pulses back and forth on a diagonal. Geometric separation alone cannot create rotation. The system requires temporal separation to break physical symmetry. Tesla's intervention was to insert the condenser, the historical term for a capacitor, into one parallel circuit. This utilizes capacitive reactance, an effect where a capacitor resists changes in voltage, forcing the current to shift ahead of the voltage in time. By dropping a condenser into circuit B, Tesla alters the timing. It stores and releases the charge, shifting the current wave out of sync. This deliberate phase shift means circuit B now leads. When circuit A is at 0, circuit B already hits its peak. One electrical source entering the motor has been split and delayed, yielding two distinct out-of-phase currents. The condenser breaks the temporal symmetry of the single-phase line, artificially synthesizing a two-phase power supply entirely within the motor casing. Operating out of phase, circuit B hits maximum current while A sits at 0. The magnetic vector points toward B's horizontal coil. A quarter cycle later, A rises to maximum, sweeping the vector 90 degrees. The cycle continues, driving a smooth circular path. Tesla defined this continuous, sweeping force as the resultant attraction. Today, we know it as a rotating magnetic field. By combining geometric coil placement with a condenser's capacitive phase shift, Tesla achieved a self-starting motor running on a single, unmodified AC power line. While the mathematics were sound, deploying this motor in the late 19th century required materials that were not yet commercially viable. Tesla documented the primary drawback of this design, citing the great size and expense of condensers for this purpose. To handle the massive currents required to generate industrial torque, the physical surface area of the condenser plates had to be enormous. The dielectrics available at the time forced these early condensers to be bulky and fragile, making them cost-prohibitive for large-scale production. This design was mathematically sound, but manufacturing technology would need to catch up before it reached industrial scale. That alignment arrived in the 20th century as advancements in polymer films and electrolytic manufacturing solved the condenser size problem. Today, the architecture Tesla outlined is the blueprint for the capacitor start or split-phase motor. This specific motor architecture operates anywhere a single-phase wall outlet must start heavy rotational loads, including refrigerator compressors, large HVAC fans, and industrial power tools. Tesla's achievement was the ability to manipulate electrical time to create mechanical motion. The capacitor motor stands as a demonstration of Tesla's ability to manipulate the physics of existing constraints, forcing a single-phase world to spin.
In the late 1880s, Nikola Tesla published extensive research on the mechanics of alternating current motors. Electrical engineering at the time was a raw, experimental discipline. Inside cluttered laboratories packed with dynamos and wire, inventors were attempting to reliably extract mechanical power from electrical currents. The primary tool for this task was the induction motor. It relies on two main components: the stator, which is the stationary outer ring of electrical coils, and the armature, or rotor, which is the inner metallic core that spins. This machine generates mechanical rotational force entirely through magnetic interaction. A current passes through the stator to create a rotating magnetic field, which pulls the inner armature along with it. However, engineers faced a strict physical constraint. For any given power supply and motor size, there is a hard, finite limit to the total electrical energy that can be expended to create those fields. Early designers approached this limit using assumptions carried over from direct current motors. They believed the primary field, the stator, had to be massive and dominant to prevent the armature from distorting the overall magnetic field. Alternating current systems operate under different dynamics, where applying those older rules severely limits mechanical output. This created a specific optimization problem. If an engineer has a fixed energy budget, how exactly should they divide it between the stator and the rotor to extract the maximum amount of physical work? Solving this precise energy allocation problem was the necessary step to turn the alternating current motor from a theoretical laboratory curiosity into a viable industrial machine. Tesla's baseline maps a motor with a fixed energy budget of exactly 100 units across field and armature energy. Early designs allocated 90 units to the field and 10 to the armature. But torque is calculated by the product of these interacting magnetic energies. To find the output for this highly asymmetric split, we multiply 90 by 10. The result is an interactive force of 900 units. Tesla abandoned the dominant primary field entirely, shifting the internal energy balance to perfect symmetry, an exact 50-50 split. The total energy sum remains exactly 100 units. The strict engineering constraint is intact. Now we calculate the mechanical output for the new split by multiplying 50 by 50. The resulting interactive force is 2,500 units. By shifting the internal ratio from 90 to 10 to 50 to 50, the mechanical output jumps from 900 to 2,500 units. By reallocating the internal magnetic energy, Tesla's geometric optimization yields nearly 3 times the physical force, without adding a single watt of external power. Applying this mathematical proof meant changing how actual motors were built. Early physical models required distinct heavy copper windings to manage this new distribution. The amount of magnetic energy generated by the field and the armature is dictated directly by the physical arrangement and density of these copper coils. This cross-section shows the outer stator coils, calculated to output exactly 50% of the magnetic energy budget. To complete the equation, the inner armature must induce a perfectly mirrored set of flux lines matching the stator's output. This introduces a complication. The stator receives its power directly from an external electrical source, but the armature does not. The armature's power must be induced. The magnetic energy has to transfer across the empty air gap separating the two components. This induction relies entirely on relative motion and rotational speed. Because rotational speed is variable, the armature's induced magnetic strength is a highly dynamic value that constantly shifts during operation. Achieving peak efficiency requires calculating the dynamic, invisible flux interaction across a physical void, rather than simply gauging copper thickness. Tesla recognized a crucial caveat to his design. This perfect 50-50 magnetic parity cannot exist at all times. When a motor starts from a dead stop, it exists in a volatile, highly asymmetric state. Massive electrical resistance and high-induced rotor currents warp the magnetic field before the machine gains momentum. As the motor accelerates, the magnetic ratio shifts continuously, moving from 80-20 down to 70-30 as rotational slip decreases. Rotational slip is the difference in speed between the rotating magnetic field and the physical rotor. Engineers design these machines for a normal operating load. This is the specific, continuous mechanical resistance the motor is built to drive, like turning a massive factory lathe or running a water pump. This chart demonstrates the design goal. The 50-50 coil layout is meticulously calculated to snap into perfect alignment only at the precise moment the motor hits this intended load speed. If the motor is severely overloaded or underloaded beyond its design parameters, the symmetry breaks. The torque efficiency plummets right back toward the 90-10 scenario. Mastering this exact state of equilibrium allowed alternating current polyphase motors to scale up, eventually powering the massive, predictable machinery halls of industrial infrastructure. Tesla's overarching engineering philosophy was that relying on brute force and dominant primary components is inherently wasteful. A properly designed induction motor maximizes its output by relying entirely on perfect system-level symmetry at the exact moment the physical work is being done. To get a massive metal rotor to spin from a dead stop, the system must overcome static inertia. Applying a force that merely vibrates back and forth leaves the rotor shuddering in place, unable to initiate a continuous rotation. This is a mechanical hurdle when using single-phase alternating current. In a single-phase circuit, electricity flows in one direction, drops to zero, and then reverses direction over a single cycle. This motor-stator cross-section shows a single phase. The magnetic vector pulses vertically, flipping polarity, but never leaving its linear path. A stationary rotor placed inside is tugged in opposite directions simultaneously, producing zero net starting torque. Engineers often prefer single-phase systems because they only require 2 wires, making them the most cost-effective architecture for long-distance power distribution. Single-phase power provides a highly efficient grid, but the physics of its linear pulse cannot provide the spatial rotation needed to start a motor. The standard solution to this problem is the polyphase, or double current system. By introducing a second independent phase offset from the first, the magnetic field can be made to physically rotate, dragging the rotor with it. Modern engineering typically treats these as 2 separate, immutable categories. A motor is designed to operate as either a single-phase machine or a polyphase machine, and that electrical identity rarely changes. Nikola Tesla's Chapter 9 text directly challenges this rigid distinction. He states, "The motor is thus transformed from one operated by the action of 2 or more independent energizing currents to one operated either by a single current or by several currents acting as one." Tesla's procedure is to start the motor with a double current to gain momentum, and then, once it is running, physically switch the internal circuit connections to run on a single phase. We are left with a conflict in the mechanics. If a single-phase field cannot provide torque to start the rotor, we must explain how it sustains the spin once the rotating field is removed. Tesla viewed the motor not as a static object, but as a dynamic reconfiguration of magnetic topography. To understand how this works, we have to look at phase 1 of Tesla's sequence, the action of 2 independent energizing currents. This diagram shows the starting electrical state. Current A and current B are flowing into the motor simultaneously, but they are offset by exactly 90 degrees. As current A peaks on the graph, it generates a strong vertical magnetic vector in the stator. At this same moment, current B is at 0 and contributes no magnetic force. A quarter cycle later, current A drops to 0 and the vertical vector vanishes. Simultaneously, current B reaches peak, creating a bold horizontal vector. When these currents run together, we apply the principle of vector addition. While the vertical and horizontal forces pulse individually, their combined mathematical sum results in a third vector. This resultant vector smoothly rotates in a perfect 360-degree circle around the stator gap. This rotating vector acts as a magnetic crank. When a rotor is placed in the center, it is pulled along by the field, slowly accelerating as it chases the rotating flux. The polyphase start creates a kinetic, rotating environment that physically compels the rotor to move. Before Tesla alters the circuit, the rotor must reach its target velocity, synchronous speed. Synchronous speed is the point where the physical rotations per minute of the metal rotor match the rotational frequency of the magnetic field. As this diagram shows, the poles of the metal rotor are now perfectly aligned with the rotating stator vector. At this speed, the rotor is magnetically locked to the stator's field. Tight lines of magnetic flux tether the two together, behaving like rigid, invisible spokes on a spinning wheel. At this velocity, the energy required to overcome the initial static inertia has already been spent. The system has achieved kinetic equilibrium, reaching the specific moment where the electrical architecture can be transformed. With the motor at full synchronous speed, Tesla executes the transformation. The independent phase feeds are disconnected. The circuit is rerouted so that the stator coils are fed by a single incoming alternating current line. The immediate electromagnetic result is the collapse of the rotating field. The smooth circular vector is replaced by a single vertical vector pulsing rigidly up and down. Since a pulsating field governs new torque at a standstill, the question is why the spinning rotor does not immediately stall. The answer lies in angular momentum. The spinning rotor's mass carries enough momentum to coast through moments where the alternating current pulses through zero. Because the rotor is already at synchronous speed, its poles align with the stator's pulsing field at the exact microsecond the current reaches its peak. The pulsating field delivers timed kicks of torque that maintain the rotor's established rhythm. The rotor's kinetic energy acts as a mechanical second phase, allowing a single alternating current to sustain a spin it could never have initiated. This side-by-side comparison shows the machine's two operational states.
On the left, a 4-wire system creates rotation. On the right, a 2-wire system creates a pulse, yet the rotor speed remains identical in both. This compromise uses the rotating vector to overcome static inertia, then switches to the alternating vector for long-term transmission simplicity. This operation bridges the gap between the two separate motor classes established in standard engineering practice. Tesla's Chapter 9 text treats the stator as a programmable matrix of flux. By manipulating magnetic topographies in real time, Tesla demonstrated that the operational laws of a machine can be rewritten while that machine is still running.
Heat and magnetism are natural adversaries. Expose a magnetized material to high enough temperatures, and the thermal energy will literally neutralize the magnetic field. In the early 17th century, the physician Dr. William Gilbert documented this exact phenomenon, noting that a lodestone or iron bar exposed to extreme heat loses its ability to attract. Thermal energy agitates the iron's atoms. This forces magnetic domains out of alignment, dissolving the magnetic force until the iron drops its load. Remove the heat, and it reverses. Cooling restores structural order and permeability, pulling the object back. For nearly 300 years, physicists treated this thermal decay as an annoying material quirk, a natural limitation that degraded magnetic performance, rather than a physical mechanism to be exploited. Nikola Tesla looked at the exact same thermal decay and saw an untapped engine. The engineering problem was how to take a static material property, iron's temporary loss of magnetism, and trap it in a continuous, self-sustaining mechanical cycle. Instead of building traditional motors that relied on rotating electromagnetic fields and physical commutators, Tesla focused entirely on the thermodynamic manipulation of magnetic flux. If applying heat could reliably toggle a magnetic field off, and removing heat could toggle it back on, that thermal energy could completely replace the mechanical components used to drive a motor. To test this, Tesla built a prototype thermomagnetic oscillator using just 4 components: a permanent magnet, an iron armature, a continuous heat source like a gas flame, and a tension spring. In its resting state, the magnetic attraction is stronger than the spring. The magnet holds the iron armature directly over the heat source. As thermal energy penetrates the iron, its temperature rises. The magnetic field lines connecting the permanent magnet to the armature rapidly dissolve. With the magnetic pole neutralized, the tension spring suddenly becomes the dominant force in the system. It violently contracts, snapping the heated armature away from the flame. Removed from the heat source, the iron begins to shed its thermal energy into the surrounding air, rapidly cooling and regaining its magnetic permeability. The restored magnetic field overpowers the tension spring, dragging the iron armature back into the flame to restart the cycle. This prototype proved that thermal energy could drive a mechanical oscillator via magnetic modulation, but the tension spring was an enormous drag on the system, consuming a massive amount of the mechanical work just to pull the armature back. Springs are passive energy sinks. They absorb the kinetic energy generated by the system rather than contributing to it. Tesla needed a way to return the heated armature to the flame without wasting the engine's output fighting against a mechanical spring. His solution was the coupled armature system. He removed the spring entirely and replaced it with a second piece of iron. This new engine positioned 2 iron armatures on a physical link, balanced on a central pivot, like a seesaw, inside the magnetic field. A single heat source sits under just one side. At the start of the cycle, armature A is positioned over the flame, glowing hot and losing its magnetism. Armature B is positioned away from the flame, remaining cool and highly magnetic. Because armature B is cool, the permanent magnet exerts a powerful attractive force on it. As the magnet pulls the cool armature B downward, the physical link connecting them actively yanks the hot armature A up and out of the flame. Now their roles reverse. Armature A cools in the ambient air and regains its magnetism, while armature B absorbs heat and loses its attraction. The thermal and magnetic states constantly swap back and forth across the pivot, creating a continuous, violent mechanical oscillation. By coupling the armatures, Tesla eliminated the mechanical waste. The cooling iron itself became the active driving force, yielding a highly optimized, self-driving thermal engine. Mechanical motors were only a stepping stone. Tesla's ultimate objective was the direct generation of alternating electrical current from heat.
This requires leveraging Faraday's law of induction. Faraday's law is a principle of electromagnetism, stating that an electrical current is induced in a conductor only when it is exposed to a varying magnetic field. Standard dynamos and Tesla's theoretical pyromagnetic approach achieve this variation in completely different ways. Industry dynamos rely on physical rotation. They spin a copper coil through a static magnetic field to create that necessary variation. Tesla's design replaces the spinning parts with a stationary coil wrapped around a solid iron core. Tesla reasoned if heating and cooling varies the magnetic field, rotating the coil is unnecessary. By rapidly fluctuating the iron core's temperature, the magnetic lines of force naturally expand and collapse on their own, moving across the stationary coil. This invisible expansion and contraction of the magnetic flux directly induces an alternating current in the surrounding wire helix. The final electrical output is identical. Thermodynamic fluctuation can entirely replace mechanical movement to achieve solid-state electrical induction. However, this solid-state pyromagnetic generator faced a severe physical constraint: the frequency bottleneck. The amount of electrical power generated by induction is directly proportional to the rapidity of the magnetic changes. Faster fluctuations mean more power. Relying on passive air to cool a solid block of hot iron takes time. The thermal exchange is far too slow to generate a high-frequency alternating current. To force extreme temperature differentials at a high cycle rate, Tesla introduced active forced fluid cooling. The iron core is sealed inside an insulated heat chamber and repeatedly blasted with injected steam to instantly strip away the thermal energy. Stripping the heat away in milliseconds allows the magnetic flux to collapse and expand at a massively accelerated rate. By weaponizing steam to force rapid thermal cycling, Tesla circumvented the physical cooling limitations of iron, unlocking the high-frequency electrical output required for a viable generator. From a crude, spring-loaded mechanical oscillator to a highly optimized coupled motor to a completely solid-state steam-cooled generator, engineering these generators required a precise mastery of thermodynamics. The absolute ceiling of the system's efficiency is strictly bounded by the rate at which heat can be injected into and extracted from the iron core. Tesla's work in this sector follows the strict logic of first principles engineering. By stripping away moving parts, he engineered a way to convert thermal energy directly into electrical current through the invisible breathing of magnetic flux. When two alternating currents are designed to peak out of phase with one another, they generate a rotating magnetic field. This animated diagram shows how that field acts on a rotor. The magnetic vector arrows chase each other in a continuous circle, dragging the metal cylinder along with them. This generates physical mechanical torque without the need for complex sparking commutators. But generating motion at the source is only half the engineering equation. Before this energy can do work, it has to be transported from the power plant to the factory. To push electrical power over long distances without losing the energy to heat, you have to transmit it at extremely high voltages. That requires a transformer to step the voltage up at the generator and then step it down at the destination. Doing this for multiple out-of-phase currents simultaneously presents a unique physics challenge. Nikola Tesla recognized that the exact same polyphase principles driving his motors could be applied directly to the construction of static transformers. In Chapter 23 of his foundational text, The Inventions, Researches, and Writings of Nikola Tesla, he laid out the blueprint for this new architecture. Translating this mechanical torque into high-voltage electrical transformation required shifting from a moving mechanical rotor to a static, unbroken geometric structure. Early single-phase transformers relied on simple linear or disjointed physical iron structures to link their primary and secondary wires. These designs suffered from severe magnetic bottlenecking. The iron path was inefficient, leaking flux into the surrounding air when placed under heavy or complex electrical loads. If you attempt to feed multiple out-of-phase currents into these disjointed cores, the separate magnetic fields clash and directly interfere with one another. Tesla's thesis solved this by altering the underlying architecture. He argued that the physical structure must be built around an iron core closed entirely upon itself. This diagram illustrates the shift. By morphing a disjointed block into a continuous, unbroken iron ring, the magnetic flux is perfectly contained.
To step up polyphase voltages without the fields canceling out, the physical geometry of the transformer has to perfectly mirror the continuous mathematical symmetry of the alternating currents. This animated diagram builds the polyphase transformer from the ground up, starting with the bare iron ring as the foundational substrate. This closed geometry provides an uninterrupted path for the magnetic flux to travel, circulating continuously through the metal without ever hitting an air gap. But a solid block of iron introduces a new problem: parasitic eddy currents. Eddy currents are localized, swirling loops of electrical current, induced within a solid conductor by a changing magnetic field. When the iron is subjected to alternating fields, specifically the high-frequency shifts of a polyphase system, these microscopic swirling currents multiply rapidly. Because iron has electrical resistance, these swirling currents dissipate energy as heat. Over time, they destroy the core's efficiency and eventually compromise its structural integrity. Tesla's structural solution to block these currents was lamination. Watch the model. The solid iron ring is split into hundreds of thin, stacked concentric sheets. Each layer is separated by a microscopic boundary of insulation. This laminated ring provides the perfect physical substrate. It successfully guides the primary magnetic field infinitely forward, while starving the destructive eddy currents of the continuous spatial volume they need to form. With the substrate built, we can introduce the electrical inputs, starting with the primary coils. A single-phase alternating current passing through this primary coil generates a magnetic flux that expands and collapses with the voltage. To extract this energy at a higher voltage, the secondary coils must be placed in direct magnetic proximity to the primary. The secondary coil wraps directly over the primary, capturing the changing flux to complete the phase A circuit. This setup handles a single phase. Polyphase transformation requires a second parallel system. Notice the phase B primary coils, wrapped at a strict 90-degree offset. The thinner secondary wires wrap directly over these new primaries, completing a 4-node architecture. This precise 90-degree geometric spacing is the physical manifestation of the polyphase mathematical offset. It sets the stage for two currents to be transformed simultaneously without interfering. Look at the dual AC waveforms to trace the real-time current. When phase A reaches peak current, it generates a maximum horizontal magnetic vector. Phase B is at 0. As phase A drops, phase B's current rises, generating a vertical vector. The core advantage of the polyphase system is found in its geometry. Because of the continuous ring and 90-degree placement, these out-of-phase fluxes never collide. Instead, the magnetic vectors sum geometrically, combining into a single constant magnetic flux that physically rotates 360 degrees through the stationary iron. This rotating flux perfectly induces stepped-up alternating currents in the secondary coils, eliminating the inefficiencies and magnetic bottlenecks of separate single-phase transformers. Pulling back from this animated model reveals the macro-level architecture of a complete Tesla polyphase grid. The generation side of this grid is anchored by massive two-phase alternating generators, specifically engineered to output these perfectly offset currents. The conceptual symmetry of the system is absolute. The static transformer acts as the exact electrical analog to the mechanical induction motor. By utilizing the closed ring, the precise phase relationships created at the generator survive the high-voltage transmission process completely intact. This complete system proved its scalable viability to the world at the 1893 World's Columbian Exposition in Chicago. Tesla's polyphase system operates as a lesson in spatial architecture. It relies on a continuous, unbroken manipulation of rotating magnetic geometry, from generation through transformation directly into final mechanical work. In the summer of 1893, visitors to the Chicago World's Fair saw something few human beings had ever witnessed at this scale. Entire city blocks, monuments, and reflecting pools were intensely illuminated against the night sky. This glowing architecture served a highly specific commercial purpose. It was the final public battlefield in the War of the Currents, a bitter fight between competing electrical standards. At the time, global power distribution was severely restricted by direct current, or DC. DC power plants could only push electricity about a mile before the voltage dropped off, meaning you needed a noisy, coal-fired power station in almost every neighborhood to keep the lights on. To power this massive fairground, an engineer named Nikola Tesla and his financial backer, George Westinghouse, won an impossible bid. They promised to run the entire exposition using alternating current, a system capable of transmitting high-voltage power over vast distances. Over 27 million people would visit the fair. If the Westinghouse generators failed, or if the lights flickered and died under the load, alternating current would be deemed a public hazard and the technology set back for decades. By day, the sheer physical footprint of the Columbian Exposition became clear. Keeping the massive pavilions and central lagoon operational required a sprawling, continuous network of energy. The source of that energy sat tucked away from the pristine neoclassical facades, deep inside the industrial epicenter known as Machinery Hall. We know exactly what sat inside the specific exhibition room because it is strictly documented in Chapter 42 of the historical record, the Inventions, Researches, and Writings of Nikola Tesla. The floor plan of Machinery Hall contained two distinct technological displays. One was a massive practical solution to an immediate crisis, and the other was an experimental leap far beyond the 19th century. The practical solution belonged to the partnership between Tesla and George Westinghouse. Together, they installed a sprawling 12-generator display specifically engineered to carry the heavy electrical load of the fair. 12 massive two-phase generators functioned as a single unified system, feeding a centralized power grid branching to 100,000 lamps. This polyphase system relies on multiple alternating currents, whose waveforms overlap, smoothly transferring energy without interruption. Crucially, this setup easily ran commercial motors alongside the light bulbs. It proved that alternating current could handle the heavy, brute force labor required by industrial machines. The economic implications were immediate. Factories moved away from rivers. Urban centers rapidly expanded outward, making overnight factory shifts reality. Those 12 generators in Chicago operated as a highly visible, undeniable proof of concept. Alternating current was ready for global deployment. Yet, just steps away from the heavy iron and roaring turbines of the Westinghouse display sat a small, unassuming table labeled simply Mr. Tesla's Personal Exhibit. Where the main hall featured brutal mechanical force, Tesla's personal table was lined with delicate, sparking apparatuses crafted from glass and fine wire. Here, he displayed working models of his mechanical and electrical oscillators, devices designed to take standard electrical currents and vibrate them into incredibly high frequencies. He used these tools to demonstrate disruptive discharge. Instead of flowing through copper wire, the electricity broke the boundaries of its container, arcing into the air. For a 19th century audience, watching this purple plasma shoot freely bordered on magic. But for Tesla, it was hard physics. He was obsessed with pushing frequencies intensely high, so power could eventually be transmitted wirelessly through the ether, eliminating the physical grid entirely. The Westinghouse generators were busy powering the reality of the 1890s, while that sparking tabletop offered a direct preview of the wireless technology we use today. When the Columbian Exposition finally closed its doors, the intense public skepticism surrounding alternating current had completely vanished. The standard had won. The flawless execution in Chicago led directly to Tesla and Westinghouse securing the highly coveted contract to harness the hydropower of Niagara Falls. As this map illustrates, the decades that followed saw a rapid, aggressive expansion. Pulsing nodes of AC power connected and illuminated, spreading outward from North America across continents. The specific polyphase system validated in Machinery Hall became the undisputed architectural foundation for virtually all global electrification. Reading through Chapter 42 of his technical writings, that single exhibit space perfectly encapsulates Tesla's dual legacy. On one side of the room, he provided the practical, heavy-duty tools required to drag society into a mechanized industrial age. On the other side, his personal experiments proved his mind was already calculating the physics of wireless data and power transmission. He was an engineer operating concurrently in two timelines, building the physical infrastructure of his present reality while prototyping our distant future. The 1893 World's Fair proved that the modern world was born twice, first in the copper wires that lit the night, and immediately after in the dream of tearing those wires down. We place a sealed glass bulb inside a copper coil, Apply a current, and watch a vibrant ring of plasma ignite inside the glass without a single physical wire connecting the two. This phenomenon relies on electromagnetic induction, setting up an electromagnetic force, or EMF, inside a vacuum tube. EMF is the electrical action produced by a non-electrical source, in this case, a changing magnetic field. The plasma forming inside the glass is entirely controlled by the atmospheric conditions outside of it. To understand the mechanics of this induction, we have to isolate the exact relationship between the gas pressure, the electrical impedance, and time-varying magnetic fields. In 1891, engineering journals were consumed by a debate over the mechanics of high-frequency electric discharges operating in vacuum tubes. Physicist J.J. Thomson approached the problem theoretically, working to map the mathematical boundaries of these glowing gases. Nikola Tesla took an empirical route. He built physical models to prove that these fields were highly sensitive to microscopic changes in their immediate environment. One specific apparatus, known as the bell jar experiment, isolates this environmental sensitivity. It reveals how a vacuum can be manipulated to act as a perfect electromagnetic shield. This engineering debate sought to define the invisible, conductive properties of empty space itself. Tesla's baseline setup, recorded in his notes, places a partially exhausted glass bulb inside a primary spiral coil made of a few turns of wire. This diagram shows the cross-section of the baseline apparatus. Driving a rapidly alternating current through the primary coil creates rapidly expanding and collapsing magnetic field lines. According to Faraday's law, that changing magnetic field induces a rotational electric field inside the glass bulb. Faraday's law of induction states that a changing magnetic field will induce an electromotive force in a conductor. This induced EMF accelerates free electrons inside the bulb. They collide with trace oxygen atoms, ionizing them and creating a visible purplish discharge along the vector path. For an induced current to form in a gas, the time-varying magnetic field must be strong enough to overcome that gas's specific ionization energy. To introduce the variable of pressure, the already exhausted inner bulb is placed inside a larger sealed glass bell jar connected to a vacuum pump. Look at this schematic of the nested setup. The primary coil is now wrapped around the outside of the larger bell jar, physically separating it from the inner bulb. The digital pressure gauge for the outer jar reads exactly 1 atmosphere. At 1 atmosphere of pressure in the outer jar, firing the primary coil causes the inner bulb to ignite normally. The space between the jar and the inner bulb remains dark. At atmospheric pressure, the outer air is extremely dense. The free electrons in that space have a very short mean free path. The mean free path is the average distance a particle travels before colliding with another molecule. They cannot build up enough kinetic energy to achieve ionization. Because this dense air cannot ionize, it acts as a strict electrical insulator. The magnetic field passes right through it. At standard atmospheric pressure, the surrounding gas is electromagnetically transparent, allowing the innermost vacuum to act as the path of least resistance. The active variable is finally introduced when the vacuum pump begins steadily extracting air from the outer bell jar. In this diagram, as the pressure drops in the outer jar, the luminous discharge inside the entirely separate inner bulb grows fainter. At a critical point of partial exhaustion, the inner bulb goes completely dark. No discharge is visible anywhere in the setup. Skeptical. Removing insulating air from the outer chamber somehow causes the inner chamber's induction to fail. The changing density of the surrounding gas alters the total electrical impedance of the system, directly disrupting the transfer of energy. The pump continues to run, pulling the bell jar into a state of high exhaustion. Watch the diagram as the pressure nears zero. The secondary discharge reappears, but its physical location has shifted into the cavity space between the inner bulb and the outer bell jar. The inner bulb remains completely dark, while the new outer plasma ring glows brightly. Lowering the air pressure in the bell jar lengthened the mean free path of its electrons, which steadily lowered the breakdown voltage of that specific cavity. The rarefied air in the outer jar is now a better conductor than the sealed vacuum inside the inner bulb. It hijacks the induced current.
An induced high-frequency current will invariably form in the region of lowest electrical impedance. The primary coil's magnetic field lines push inward. The outer plasma ring functions as a gaseous Faraday cage, blocking electromagnetic fields. Induced currents within the outer jar create an opposing magnetic field, perfectly canceling primary field lines before reaching the inner bulb. This opposing field effectively and completely shields the interior bulb from the primary coil's influence. The outer plasma absorbs the energy. High-frequency induction is regulated by the spatial distribution of impedance. The Tesla-Thomson debate proved the extreme sensitivity of electroless discharges. Thomson subsequently documented that straight conductors, varying pressure gradients, and specific inductive capacities drastically alter the formation of these fields. Tesla's bell jar experiment physically proved that in high-frequency physics, empty space is never truly empty. Governed entirely by the conductive properties of its molecular density, a vacuum will serve as either a transparent window or an impenetrable electromagnetic shield.
May 20th, 1891. Inside a darkened hall at Columbia College, a man holds a sealed glass tube. There are no wires attached to it, no metal contacts. When power surges through the room, the tube bursts into brilliant, glowing light. The man holding the bulb was Nikola Tesla. He was presenting his latest research to the American Institute of Electrical Engineers, a gathering of the top minds in the field. Surrounding him in the lecture hall were heavy wooden tables covered in massive induction coils, copper wire spirals, and humming generators. This equipment looked nothing like the standard electrical tools of the day. Until this point, generating light required direct physical connections. By removing the wires and illuminating a bulb through open air, Tesla forced the scientific community to look past traditional circuits, pointing them toward the invisible properties of the electromagnetic field. At the time, electricity was treated as an industrial workhorse. Engineers were entirely focused on building massive grinding motors and continuous current dynamos to push basic power from a generator to a factory floor. Tesla broke from that heavy industrial mindset by introducing high-frequency and high-potential currents. Instead of sending slow, heavy pulses of energy through a wire, he generated electrical waves reversing direction tens of thousands of times per second, while pushing the voltage to extreme heights. To prove this highly charged energy was controllable, he subjected his own body to it. He sat calmly next to a giant transmitting coil, while hundreds of thousands of volts ripped through the open air, bridging the gap around him. The sheer scale of these discharges proved that the ether itself could conduct immense energy. The rules governing standard direct current motors simply could not explain what was happening on that stage. Within days, reports of the Columbia College demonstration crossed the Atlantic. The European scientific elite immediately demanded an opportunity to see these high-frequency effects in person. Through early telegraph lines, the raw data of Tesla's experiments spread to laboratories in London and Paris. It created a surge of international demand for his mathematical and physical methods. By February 1892, Tesla had crossed the ocean to deliver a highly anticipated lecture in London, standing before an entirely new continent of researchers. His audience included physicists who had spent their lives studying radiant matter and electromagnetism. These researchers were trained to look for strict empirical proof. This visit functioned as a rigorous scientific audit. Tesla had to show his peers exactly how his high-frequency circuits were built, proving his claims about wireless power transfer through strict mathematical reality. The scrutiny continued as he returned to the United States, taking his presentation to the Franklin Institute in Philadelphia and then St. Louis in 1893. Across these cities, his primary goal was transparency. He was systematically laying out the chief results of his investigations, effectively open-sourcing his research so other scientists could test it for themselves. To do this, he brought his custom disruptive discharge coils and high-frequency transformers onto the stages, powering up bulbs right in front of the crowd to physically anchor his theories. He detailed the exact wire gauges, the required number of turns in the primary and secondary coils, and the precise insulation methods used to contain the high voltages. He gave them the exact instructions required to replicate his work. This 3-year tour effectively served as a massive, deliberate data transfer. Tesla handed the global engineering community a practical, tested roadmap for managing extreme electrical currents. While the massive electrical arcs drew the most public attention, Tesla's own notes reveal that the most critical finding from this entire period of research was much smaller in scale. The true breakthrough centered on his experiments with phosphorescent bulbs. These are glass tubes containing specific gases that glow when exposed to electromagnetic radiation. This chart plots energy input against light output. Tesla discovered he must dial in the voltage to a definite potential to hit this exact peak. Here, wasted heat drops away, but luminosity stays maximized, yielding the most economical light physically possible. By identifying this exact voltage threshold, he proved that the future of light relied on precision electrical tuning rather than brute force generation. That single discovery regarding phosphorescent efficiency validated the exact methods he had been sharing across New York, London, and Philadelphia. The printed records of these lectures became a permanent, valuable guide. They provided the foundational math and the physical blueprints for an entire generation of researchers entering the new territory of high-frequency electricity. By proving that extreme frequencies and finely tuned potentials could generate light without wasted heat, Tesla's work steered global engineering toward the efficient systems we use today. To create continuous mechanical motion using electricity, early engineers faced a physical paradox, forcing electrical current into an object spinning at high speed. The standard solution was direct physical contact. Engineers used spring-loaded carbon blocks, called brushes, and rotating copper segments, called commutators, to maintain a continuous sliding connection with the spinning armature. This sliding contact creates kinetic friction, generates heat, and causes the mechanical degradation of the carbon brushes through spark pitting. This friction acts as a strict mechanical ceiling on motor efficiency and speed. Electrical energy is lost as waste heat, and the physical components wear down. Magnetic fields, however, exert force across empty space without friction. This raises a precise engineering question. Is a physical wire connection required to transmit electrical power to a spinning rotor? As long as electric motors rely on direct physical conduction, their output is restricted by the mechanical friction of their own electrical contacts. In the late 19th century, Nikola Tesla proposed a design that abandoned conductive motor contacts. Outlined in Chapter 19 of his collected lectures, Tesla's design required the complete elimination of electrical contact with the rotor. His replacement architecture relied on inductive effects in permanently closed circuits. Instead of wiring the spinning core to a power source, the armature is wrapped in continuous closed copper loops, connecting to nothing but themselves. This geometry introduces a permanent physical air gap that separates the electrical power supply from the rotating mass. We need to map the exact electromagnetic physics required to force power across that empty gap. Tesla's design used the empty space of the air gap as the primary bridge for energy transfer. The physical teardown begins with the stationary outer ring of the motor, known as the stator, housing the primary coil windings. We apply alternating current, or AC, to these primary coils. This current generates a magnetic field within the hollow central cavity of the stator. Because the current alternates, this resulting magnetic field is not static like a standard permanent magnet. The field expands, collapses, and reverses polarity in synchronization with the alternating power supply. We measure this invisible, moving force as magnetic flux. Magnetic flux is the total magnetic field passing through a given surface area over a specific time. This dynamic, shifting environment is the absolute prerequisite for contactless power transfer. The primary coils act as a dynamic transmission array, radiating electromagnetic energy directly into the void. We now introduce a single permanently closed loop of copper wire into this pulsating field to represent the armature. This loop is electrically isolated. It has no physical connection to the primary coils, the power grid, or any external battery. The governing physics principle here is Faraday's law of induction. This law states that when a conductor experiences a changing magnetic environment, a voltage is generated within that conductor. As the blue flux lines from the primary sweep across the physical boundary of the copper loop, they cut the conductor. This cutting action induces an electromotive force, or EMF, inside the copper wire. EMF is the voltage produced by a changing magnetic field. Because Tesla designed this as an unbroken, closed circuit, the EMF has a continuous path to follow, generating an electrical current. The closed copper loop has extremely low electrical resistance, resulting in a massive induced current. Power flows from the grid to the primary coils, crosses the air gap as magnetism, and converts back into electricity inside the isolated loop. The armature harvests its power directly from the surrounding changing environment. With current flowing inside the closed loop, we must now convert that electrical energy into mechanical motion. Any conductor carrying an electrical current generates its own magnetic field. Now this brings us to Lenz's law. Lenz's law dictates that the direction of an induced current will create a magnetic field that opposes the original change that created it. The primary blue field shifts, and the secondary red field pushes back against it to maintain the physical status quo. Magnetic fields cannot occupy the same physical space without exerting force on the conductors generating them. This invisible magnetic repulsion pushes the physical copper loop, forcing it to move away from the primary field's pressure point. And this rotational push is mechanical torque. Ultimately, the induced current's opposing magnetic force is the invisible engine driving the motor's smooth mechanical rotation forward. This theoretical single loop must be scaled up to meet the demands of a functioning industrial motor. Tesla packed the rotating drum with dozens of these permanently closed copper circuits, setting them at offset angles. As the armature spins, different closed loops rotate into the path of maximum magnetic flux, ensuring continuous induction. This geometry leaves no dead spots, creates no sparking contacts, and allows no power interruptions. The primary coils perform two jobs simultaneously. They act as the power grid transmitter, and they provide the magnetic stator against which the rotor pushes. This synchronized system completely bypasses the mechanical friction of the early commutator motors. By layering these isolated inductive reactions, Tesla generated smooth mechanical power without a single point of mechanical wear. The physical air gap separating the stator and the rotor was traditionally seen as a barrier that required physical wires to bridge it. Tesla utilized the action thereof of the primaries to transform that empty space into a medium for induction. The motor functions as a physical reaction to a varying magnetic environment. The architecture relies on the interplay between Faraday's induction and Lenz's opposition. This exact geometry of inductive power transfer remains the foundational architecture for the majority of modern industrial machinery and electric vehicles. The closed-circuit armature established that empty space, when properly energized, serves as a frictionless medium for energy transfer.
By the early 1890s, Nikola Tesla was pushing electrical engineering into the extremes of high-frequency and high-potential alternating currents. Generating these rapidly oscillating currents was only useful if there was a reliable way to store and condition that energy within the circuit. This requires a condenser, or what we now call a capacitor, the critical component for electrostatic storage in high-voltage circuits. A condenser is built using two conductive metal plates, separated by an insulating medium called a dielectric. Tesla discovered a physical bottleneck. At extreme frequencies, standard condensers simply tear themselves apart. Mastering high-frequency power was a material crisis. The standard methods of energy storage had reached their physical limit. To maximize storage capacity, engineers select dielectrics with the highest specific inductive capacity. Specific inductive capacity is a physical property that measures a material's ability to store electrical energy in an electric field compared to a vacuum. Historically, this pursuit of high capacity led engineers to use dense, solid insulators like glass and sheet mica. These rigid materials perform exceptionally well under standard low-frequency or direct current conditions. The problem arose when Tesla subjected these same plates to rapidly oscillating high-voltage AC fields. Under these extreme high-frequency stress parameters, even the highest-rated solid insulators fail catastrophically and physically break down into pieces. The structural rigidity that makes glass and mica highly capacitive is the exact trait that guarantees their destruction in high-frequency regimes. To find the cause of the failure, we have to look past the macro components and zoom into the microscopic boundary between the metal plate and the solid dielectric. Even the most polished, rigid materials are not perfectly flat. They possess surface imperfections at the microscopic level. Regardless of clamping pressure, microscopic geometric voids inevitably exist between a flat metal plate and a solid glass dielectric. These voids are filled by ambient air during assembly. This air is the weak link, as its breakdown voltage is drastically lower than the surrounding glass. Because a capacitor is only as strong as its weakest microscopic gap, the high capacitive rating of the solid glass becomes irrelevant. Now consider what happens when a high-frequency alternating electric field is applied across this imperfect boundary. The electric field easily exceeds the low breakdown voltage of the trapped air pockets long before it stresses the glass. This triggers localized ionization of the trapped air, known as corona discharge, turning the pockets into pulsing plasma. This generates intense heat and produces corrosive nitrous acid. The rigid glass cannot dissipate this thermal energy, leading to thermal runaway and physical fracture. Tesla realized that to prevent this cascade, he had to eliminate all gaseous matter from his high-tension apparatus. In a solid insulator condenser, trapped air acts as a localized explosive charge that the high-frequency field triggers continuously. In Chapter 34 of his lectures, Tesla details his solution, abandoning high-capacity solid insulators in favor of a liquid medium. Tesla's design required completely immersing the condenser's conductive plates in a bath of specially selected oil. This liquid dielectric has a primary physical advantage over solid insulators like glass or mica. It possesses absolutely zero structural rigidity. The fluid dynamics of the oil allow it to conform perfectly to the microscopic topography of the metal plates. The heavy liquid oil actively displaces the ambient air, pushing it out of the condenser entirely. By removing the gas, Tesla eliminated the low dielectric weak points that caused corona discharge and subsequent failure. Liquid dielectrics solve the physical mating problem by transforming a flawed, rigid boundary into a seamless, continuous insulating medium. But we must also consider the boundary condition. What happens if the voltage spikes high enough to overcome the dielectric strength of the oil itself? In a solid insulator, a localized breakdown permanently punctures and ruins the material. A liquid insulator, however, responds to a localized breakdown arc with a different mechanism. An electrical arc in oil vaporizes a microscopic amount of the fluid, creating a small hydrocarbon gas bubble. Because it is buoyant, the gas bubble floats away. The surrounding unionized oil instantly rushes back in to fill the gap seamlessly. This repeatable phenomenon is known as the self-healing property, and it is unique to fluid dielectrics. This principle remains the foundational architecture for the modern power grid. We still submerge high-voltage transformers in insulating oil to manage thermal stress. Tesla's shift to oil was the discovery of a material optimization required to survive the physics of the high-frequency era.
When an alternating current at standard household frequencies, 50 or 60 cycles per second, strikes a grounded object, the result is violent. Engineering baseline dictates that high electrical potential is inherently and immediately dangerous to human biology. Contact with a high voltage line at these frequencies forces massive current through the body's resistance. This induces muscular tetany, locking the muscles in a state of continuous contraction, and triggers ventricular fibrillation, scrambling by heart's rhythm until it fails. In the early 1890s, Nikola Tesla presented a series of formal claims that directly contradicted these foundational safety rules. In the records of his researches, specifically Chapter 31, Tesla described passing hundreds of thousands of volts directly through his own body without suffering injury or even a surface burn. He asserted that these extreme currents were therapeutic, coining the term massage to describe the physiological effect of applying high potentials to the human frame. A generator produces currents capable of arcing through open air, yet the human body interacts with that same high potential field as if the standard rules of lethality have been suspended. Standard electrical safety analysis relies on Ohm's law, where voltage is viewed as the primary vector for pushing lethal amperage through human tissue. This chart plots electrical frequency against biological disruption. Tesla hypothesized that pushing the alternating frequency into the hundreds of thousands of cycles per second shifts the current's behavior, leading to a precipitous drop-off in disruption.
At these extremes, the system moves from electrodynamic conduction to electrostatic induction. Electrostatic induction occurs when energy transfers via rapidly alternating electric fields, rather than the physical migration of electrons through a conductor. To test this, Tesla had to move beyond the capabilities of existing hardware, inventing a new class of high-frequency generators from the ground up. Before he could decouple voltage from danger, he had to solve the catastrophic hardware failures caused by high-frequency impedance. The mechanical alternators of the 1890s relied on spinning heavy copper armatures past magnetic fields, using mechanical commutators to direct the current. Physical mass limits velocity. Spinning a metal armature fast enough to reach the hundreds of thousands of cycles Tesla required would cause the machine to disintegrate under centrifugal force. Tesla turned to a different architecture, utilizing disruptive discharges from condensers, early capacitors, to feed specially designed induction coils. These new coils introduced a critical engineering failure point: gaseous matter, or air, trapped inside the high-tension apparatus. High-frequency currents cause rapid thermal buildup, leading to dielectric breakdown, the moment an insulating material fails and allows electricity to arc directly through it. This heat would punch through standard cotton or rubber insulation, destroying the coil. Tesla's solution involved immersing the entire secondary coil, often wound with 15,000 turns of wire, inside a zinc box filled with boiled-out linseed oil. Excluding air and utilizing liquid dielectrics provided the insulation necessary to safely generate high-potential currents at extreme frequencies. With the oil-immersed coil active, the generator produced a massive high-potential output oscillating at hundreds of thousands of hertz. Tesla observed that the output no longer formed a tight, focused arc. Instead, misty white streams broke from the edges of the terminals, spreading phantom-like into the surrounding space. These streams are the manifestation of violent electrostatic bombardment, where the extreme frequency excites the surrounding air molecules until they glow. This diffuse discharge is physically distinct from the concentrated, lethal arc of a standard transformer. Relying on his calculations, Tesla placed his bare hands directly into this localized electrostatic field, exposing his body to hundreds of thousands of volts. The engineering of the oil-immersed generator had produced a physical phenomenon that allowed for direct human contact. Upon contact with the stream, Tesla noted that no sensation is produced. This forces a question of biological physics. Why does the human nervous system ignore this massive transfer of electrical energy? Nerves fire when ion channels open and close at a slow metabolic rate. A 60 Hz current aligns with this timeline. The current hits, the nerve fires, and the muscle locks. Tesla's current reverses 100,000 times per second, cycling too fast for channels to respond. While the current is moving through the tissue, the biological sensors are simply too slow to register the oscillation as a neurological event. This is the frequency physiology decoupling, the threshold where electricity ceases to trigger the nervous system, interacting with the body through entirely different physical laws. Because the energy is not causing a neurological shock, it must manifest in the body as another form of work. The rapid oscillation causes uniform molecular friction and particle vibration within the conductive fluids and tissues of the body. This vibration results in deep, uniform tissue heating, without the external burning associated with lower frequencies. This thermal effect is what Tesla called an electrical massage, an internal warming of the body achieved purely through induction. Tesla had identified a method to safely transmit large amounts of energy into biological tissue as controlled heat by bypassing the nervous system entirely. Tesla's work on high-frequency currents provided the empirical basis for the field of modern electrotherapeutics. The clinical descendant of his experiments is diathermy, a medical treatment that uses high-frequency energy to generate deep-seated heat. Modern diathermy machines utilize these same principles to bypass the nerves and apply heat for physical therapy and surgical applications. This engineering triumph transformed a lethal force into a healing modality by exploiting the far ends of the frequency spectrum. Tesla demonstrated that electrical lethality is a product of the mathematical intersection between high potential frequency and the metabolic response times of human physiology. In the late 1880s, the rollout of electrical lighting hit a severe mechanical bottleneck.
The entire industry relied on machines that were literally tearing themselves apart as they tried to meet the growing demand for power. The problem was distance. Engineers could not find a way to transmit power across large areas without losing most of the energy along the way. These early direct current systems required thick copper cables every few blocks, as they could only push electricity a mile or two from the station. To the engineers of the day, these grids were cumbrous, wasteful, and trapped by their own range. The primary cause of this waste was friction. Early generators relied on a commutator, a rotary switch that reverses the current, and brushes that physically pressed against it. This constant grinding created heat and sparking, leaking energy into the air instead of sending it down the line. By this point, the industry reached a consensus. Simply building larger versions of these generators would fail. The machines were too fragile and the physics too limited. To power a modern world, the industry had to abandon the old blueprints and find an entirely new set of mechanical principles. This created a vacuum that only a total outsider could fill. That outsider was Nikola Tesla. Born in 1857 in a borderland region of Austro-Hungary, he arrived in the industry with a mind trained to look past mechanical friction. While studying in Graz, he began working on an idea his professors called impossible, a rotating magnetic field that could spin a motor without any physical contact between parts. He initially trained as a teacher, but his obsession with this frictionless motor drove him to switch paths and fully immerse himself in a rigorous engineering curriculum. He moved through Prague and Budapest, studying languages and engineering to prepare himself for the global stage. After working in France, Tesla realized that the United States was the only market fast and hungry enough to build his radical concepts. He left Europe to seek his fortune in the American grid. This combination of rigorous Eastern European training and global ambition gave him the tools to challenge the established scientific dogma of the time. In May 1888, Tesla stood before the American Institute of Electrical Engineers in New York to present a paper that would dismantle the direct current model. He didn't come with just theories. He brought finished alternating current motors already tested in private operations. Looking closely at the axle and armature, you see the complete absence of brushes and commutators that caused old systems to fail. The secret was polyphase currents. These are multiple alternating currents synchronized to flow in a specific sequence, rather than a single continuous stream. By using multiple currents timed out of phase with each other, Tesla created an invisible rotating magnetic field. This field pushes the central rotor around purely through magnetism, removing the need for physical switches. By removing the physical components that crippled the old electrical models, Tesla proved that power could be transmitted across the country flawlessly. He had rewritten the rules of the grid. Tesla didn't stop with the motor. He barely waited for the industry to adopt his polyphase system before he pushed into even stranger territory. He moved his focus to high-frequency currents and high-potential lighting, filling his laboratory with experimental coils and vacuum tubes to test the limits of the ether. His 1891 lecture at Columbia College introduced the world to artificial illumination and electrostatic phenomena, showing a stunned scientific community that electricity could do more than just turn wheels. This work eventually took center stage at the 1893 World's Fair, where his alternating current system powered the massive, glowing displays of the Grand Pavilion. Scientists and engineers quickly realized that Tesla was blazing the path that all future electrical development would have to follow. The ultimate value of Tesla's legacy isn't found in his patents alone, but in the performance of a vigorous, original mind that dared to solve nature's most rigid engineering problems.